Unfortunately, Robert Neseler from Austria is ill. He is not able to participate. I hope he will be able at least as a participant, but not as a speaker. And instead of, we have asked Brooke Spreen from Anerdgy, which is situated in both Germany and in Switzerland, to come in with her doubling down on rooftop wind. Brooke, are you on?
Yes, I am.
Oh, that's good. And thank you for your kindness going in now. Please go on, Brooke.
Yeah, absolutely no problem. I'm happy to bump the presentation forward a little bit. Yeah, thanks so much for the introduction. As you said, our company has a presence in both Germany and Switzerland. I happen to be sitting in Zurich at the moment. That's where our R&D office is. I'm a design engineer. I'm taking the lead on this B60 project. This is our dual rotor wind turbine. Let me get the presentation up and running here. Let's come here and move this guy out of the way. All right, here we go. Yeah, okay. So what I'd like to do, I would start a little bit talking about the design process behind the B60. Then I'll like to touch on some of the component systems and finally touch on one of the regulatory issues that we've come across. Hopefully this will spark some discussion that can maybe prompt some answers later on. So to give a start here, we've had several speakers who have addressed the importance from a policy side of increasing the installation of distributed renewable energy, particularly wind and particularly micro wind. I'd like to look at this from the other side for a little bit. So if you're a homeowner or an architect, what are some of the considerations that are kind of come into play when you decide whether you want to put a turbine on your roof? One of the things that often comes up in conversation is going to be this desire to combat climate change, by offsetting fossil fuel generation. This is super, this is important. I think we need to be realistic about how many people this is going to convince to put a turbine on their roof. Depending on where you're from, depending on what the political or economic climate might be, this is possibly not going to be enough. So although this is something that wind turbines currently do well, it's going to be a prime motivator for a very small portion of the population. One of the next things we can talk about would be a desire for more resiliency or a desire for more self-reliance. Maybe there are people who they have their own microgrid. Maybe there are folks who like to be prepared in the event that the grid that they're connected to goes down. They want to still be able to power their electronics or keep basic household functions going. Again, this is important. This is something that wind does well in the moment, but it's going to appeal to a very small segment of the population. When we talk about expanding rooftop wind, micro wind, even small wind, well, let's stick more on the micro wind side. When we talk about expanding this to reach more people, we need to look at the bigger picture. So we need to look at things like, what's the daily user experience? This could be a positive thing in that people can, they can take a look at their control system. They can see, oh, look, honey, we generated however much energy today. How cool is that? And this was more than yesterday and less than the next day. And it becomes something exciting and engaging. Unfortunately, on the other side, it might be that there's a lot of noise generation, there's vibration shaking the rafters of the house, things like this that are annoying or irritating, and this tends to be more of the situation today. We can look at how easy or legal to install the rooftop wind is. So when a homeowner starts looking into the different options and they think, oh, you know what, for whatever my reasons are, I want to put up a rooftop wind turbine. And then he starts reading, what? But wait, I need to buy the turbine, that costs something. And then I need to buy an inverter, and that's how much? And oh, wait, I also need a controller. And I need to find an installer who actually knows how to deal with DC and put this into my house. And whoa, this is too much. I can't deal with it. This is a roadblock we need to address. We need to find some solutions to. Another important thing is going to be the long-term economics. So this, of course, comes into things like the payback period, what the electricity costs are, the feed-in tariff, such and such. From the engineering perspective, we need to talk about how structurally secure, what the lifetime of the product is and how much maintenance it needs, how those costs are going to affect things. To kind of pull this together, if we want to facilitate the widespread adoption of rooftop wind, we as engineers, anyone who's out there involved in this market, we need to start looking more at just the function of providing rooftop energy, of rooftop generation. We need to look at the overall design and experience. Maybe to draw some parallels with the electric car industry, I remember when my cousin got a Prius, maybe 10 years ago or so. He got it for the sake of being green, for environmental reasons. That's cool. I know some of my family members made fun of him. This was not something that they could understand. Now, if that cousin were to be driving an electric car, folks might be more willing to think of, oh, Tesla, wait, that's actually really cool. You have crazy acceleration and da-da-da-da-da, all these other values that can influence the final decision. We need to find a way to do this with rooftop wind. So this is kind of what we wanted to do with the B60. We sat down and said, okay, we need to make sure we have the function of a rooftop wind turbine. So we need some sort of significant energy generation that people are going to notice. We define this for ourselves to be about 500 to 1,000 kilowatt hours a year. For reference, the average German citizen is going to need about 7,500 kilowatt hours a year. And then equally important, probably more important, is going to be that we have reliable passive safety systems installed. This is important, I mean, for the basic reasons of we need to not hurt anyone. We need to make sure that structures are not damaged. We need to make sure that this is not a threat. But beyond our bottom line, this is important for the reputation of small wind. If companies are going to be designing rooftop wind and they're not going to be certifying them or kind of escaping or sliding under or through this gray zone that micro wind currently occupies, they need to be responsible about what they are designing and putting on people's roofs. Bad reputation can affect all of us, right? Then if we move over to the design side and we start talking about these yellow bubbles up at the top here, when we look at the long-term economics, we want to make sure we have a sturdy construction. We need to make sure that these are materials that are going to hold up to the harsh demands of UV exposure, of salt air, of extreme temperatures if we're going to go into those environments. Long lifetime, minimal repairs. On the easy and legal to install side, our ideal situation is we take this wind turbine and auxiliary electronics story, and we package it all together to a single integrated device. So we actually mount the electronics on the wind turbine, and then when installation comes along, you get your box with the wind turbine, or the installer has the box actually. He opens it up, he puts the pieces together mechanically, maybe plugs one or two things internally, but this encapsulated thing is put on the roof, and then this is directly wired into the house's AC system. This is the ideal. We're not quite there yet, but I'll talk a little bit more about it in a second. And then the daily user experience, again, no irritating noise or vibration. This is going to mean a low RPM rotor. And the kind of final point, it maybe sounds a little bit silly, but I think it's nonetheless important. We need these things to look good. Again, when we're talking about the early adopters who are super excited about green energy, it's fine if it looks kind of hacked together, a little bit less professional. It's just, they're really excited about how cool it is. When we start talking about mass appeal, appearances are going to be a bit more important. So we went through this process for the B60, and we came up with something that looks like this. What I'd like to do now is go through some of the subsystems that we have, highlight these subsystems, Although COVID, of course, has had the unfortunate impact we can't meet together, it does have a little bit of the advantage that I'm able to actually show you some of these parts here. Well, hopefully that will work out okay. I should note that these are the last prototype iteration. We're currently in our first production run, and the parts for the CAD that you will see on the screen is on its way. It's not here quite yet, but I can kind of give you a sneak preview to help an idea of how it's going on. You'll note I'm showing the inverter here on the bottom screen. This is an ETA. It's something that I will mention briefly later, but won't highlight it quite as strongly. And all of these subsystems, they kind of belong in our toolbox of technology for renewable energy generation. At Anerdgy, this is our pitched roof distributed renewable energy generation solution. So we have others, we will have more in the future. We hope we'll be able to reuse some of these subsystems. And it would also be an option that these are subsystems that other people can make use of in their design. If you're, yeah, just to mention that. So to start here with the rotor, let me take just a moment here. I would like to see if there's a way I can see what you guys can see as well. So I actually have a rotor set up here behind me. Give me just a moment. I'm going to stop sharing my screen so that I can try to get this up more together. It looks like that might not be possible on here, unfortunately. Okay. Yeah, so just going to give a quick look behind and then switch back to the presentation. This is one of our prototype rotors set up. You'll notice that there's a ring on it. This is an option we'll be exploring in the future. It's not going to be on the first iteration of deliveries, but okay. Let's come back down here. Sorry about that. So when we wanted to put together our rotor, we knew that we wanted to optimize it for low RPM. So we actually custom designed our blades. We based them off of a profile, I believe it's SD7062. This is from the University of Illinois, which puts out libraries of different airfoils. And we optimized the cord length and the twist of the blade so that we could produce 1 kilowatt at 10 meters per second, and we would have a very high startup torque. In terms of testing and such, we have taken previous issues of our prototype to a wind tunnel just across the border in Germany. This is actually a retired Airbus wind tunnel. As you can see, only one of our rotors fits actually, so we have to get a little bit creative about putting things in there. In those previous tests, we were looking at a power coefficient at this 10 meters per second, 350 RPM of right around 0.3. This is lower than what we expect in the final version. We've made some significant improvements since then, and we're actually looking forward to later this month, assuming borders are open, heading back up to that tunnel to get our final numbers. And if anyone's interested, get in contact with me. I can let you know how that goes. One of the other important systems that we have, this is our passive security brake. So we wanted to make sure that no matter what happens electrical wise, you maybe noticed that we have, I'll switch ahead for a moment here. So we have a single motor here at the bottom, and we have transmission belts that connect the two. We wanted to make sure that if these belts break, or if there's any other reason that we lose control of the rotor, that it's going to stop. To that end, we have our SBR. If you can see me here, I have an early prototype. This is a casing. Inside the casing, we have a disc brake on both sides. On the PowerPoint here, I'm going to try to point to what I'm speaking about here. And so these are the pads, and then we have the brake that's clamped between them. This whole housing is going to be bolted onto the mast, and it does not move. That's very important. So during normal operation, this guy's bolted down, the disc is locked in place, and the part that is moving is this cam. I'm showing it here on the camera. Now, if you follow my mouse, it's here on the screen. This guy is attached to the shaft with a key, and it's going to be rotating along with the shaft. Once it reaches a certain RPM, so at 400 RPM in our case, this guy is going to trigger and open up. It's the centrifugal force that throws it out. At that point, this cam is going to lock into the disc brake, and it's going to bring the rotor to a stop. This, as I said, this is an emergency brake. This is something that happens fast, but it is designed to deal with the loads that are going to be on the system. This is a key component of safety on our rotors. You'll notice also that there is a small cable coming down here. It provides the functionality that we can also trigger this brake intentionally. So someone near the base of the rotor can trigger it, or we can have a, maybe if our motor overheats, we have a wax pin that pops out and triggers it. It allows more options for incorporating this guy into our turbine. The last component I'd like to talk about is our AFI. This is our motor drive. So this guy looks like here. You can see my camera. It's quite small, as you can see. This is our controller. What we wanted to do is we wanted to take something that normally would be more like this, use the latest power electronic devices that have come out to simplify it down, put it in a waterproof casing, and stick it directly onto the back of our motor. So we have a single integrated unit that can be installed up on the B60. This is kind of the first half of realizing our dream goal of having all the electronics up on the roof. The inverter, which we hope will be finished by the end of the year, will complete that process. Some of the features of this AFI, so it has the computer on board. This means that you can have a comms line going to it. You don't have to. It can run independently. It knows what the power curve will be. It knows how to operate the rotors in cases of extreme wind, overspeeds. It can detect if there's extra vibrations, things like that. And it's going to output 390 volt DC. And maybe most importantly, this thing is fully EMC certified. So what comes out of the AFI, it's not going to be putting off any nasty EMI effects that are going to mess with the electronics in your house. That if you're worried about the health exposure related to this, there's no need to have a shielded cable or anything, just clean DC coming out. And so now that we've talked about the subsystems, I'd like to take let's check time here. Is that possible? Looks to be a little bit difficult, but I'll take the last few minutes to talk about a regulatory hurdle that we've come across recently. So lightning protection is something that is very well defined for large wind turbines. It's defined for small wind turbines in the 61400 IEC standard. When you start talking about rooftop wind, it's much more difficult to apply what they say. So if we have the example here of a house, for this talk, I'm going to focus on the case where there is no lightning protection installed. This is just your typical homeowner where the risk doesn't warrant a full lightning protection system. We want to put the B60 on top. This might ideally look something like this. Here I've taken the liberty of condensing all exterior electronics into this single box called aux. We have a plug and we have a permanent ground line that goes to the house. Now, the question is, does putting a B60 on the roof or any rooftop wind turbine, does it increase the likelihood of a lightning strike? Does it increase the damage that would be caused if lightning strikes the roof? If these things are true, is this something that we can be held liable for? What's the best practice for mitigating these things? It's difficult when you're talking about the possible catastrophic damage of a lightning strike. It's important to have a legal footing to stand on to make sure that we're doing the right thing and that this isn't something that can come back and hit the company, right? So in trying to search for best practice, this is what I've been working on the last week or two, on and off. Looked at the wind turbine standards. They are so focused on the larger options, they're not so helpful here. What we thought might be more useful was to look at rooftop antenna standards and to look at rooftop PV standards. So on the antenna, we have an IEC option. For the rooftop PV, we're focused mainly on the DEAN guidance that relates to lightning protection. When you start looking at these guys, they are in some ways useful. In other ways, it starts to make some interesting questions about business case. So with the antenna standard, for example, they say that you need to have a ground line, a conductor of 16 square mils of copper coming down to an earthing electrode. That's fine, makes sense. This is going to be an extra cost. We want to be safe, but yes, it's something to consider, right? When we look at the PV standards, there's several different cases that they offer. There's recommendations of SPDs, so surge protection devices that need to be installed in different places. And all of these things have an associated cost. Now the question is, how do we find the right balance between making sure that we're holding up the standards of best practice while also trying to keep a reasonable cost for our consumers? If we're talking about a target price for the V60, for example, of about $5,000, then if we need to add an extra grand or even $2,000 in lightning protection measures, it's not a very happy story, right? So this is one of the cases where having some sort of either regulation or white paper or guidelines that clearly outline the best practice that micro wind companies can show to homeowners, to insurers, to city planners and such, this is something that would be very useful and maybe we could talk about in the future. With that, I would like to ask for if anyone has questions, and thank you very much for your attention.
Thank you very much, Brooke. I just have a short question to everybody, because we can launch a poll if it's should be 20 or 30 minutes for a break right now. We'll launch it now, and then you can put in whether it should be one or the other. But there will be some questions for Brooke Spreen, so please come up with them now. Otherwise, we will continue after the break at 15 hours CET. But any questions now?
I would like to ask one question, please.
Yeah.
Yes.
How many square meters wind do you touch?
Well, we have the two 2-meter diameter turbines. So we're looking at 6 square meters.
Okay.
My math is still functioning.
I think they will be very difficult to have a double in Denmark. I believe a single one is possible.
Why do you think the double would be difficult?
Because I don't remember it quite, but I believe it's 3 square meters is maximum.
And above the 3 square meters, there's new regulations that kick in, or what do you mean by maximum?
No, it's actually 5 square meters swept area, which is a limitation for having an certification on the wind turbines. Okay,
and so above the 5 square meters, you need the certification. Below, you're exempt?
Yeah, and an approval, yes.
Yeah, cool. Cool. Yeah, this is something that we'll have to work on. It would certainly be wonderful to get the certifications that we need to satisfy these requirements. It'll be something to look for in the future.
Yeah, but I think it's look very interesting. How many kilowatts can you make for 1 year?
Yep. So of course this is always a difficult question, right? Because it's going to depend on the wind resource. It's going to depend on more than just the macro wind resource. It's going to depend about the local turbulence and exactly where you install the thing. But our design goal is this 500 to 1,000 kilowatt hours a year. And this is assuming that 10 meters per second is our kind of nominal operating speed.
Yeah. Thank you.
Yeah, thanks.
Thank you very much. We have just, the pool has been, we've gone through it, and there's about 50% for 20 minutes and 50% for 30 minutes. So we'll cut through and say 25 minutes, and we will have a break until 2 o'clock, and then we'll meet again. Of course, please do not exit. So if anybody wants to continue the talk, they can do so. Otherwise, we'll meet at 2 o'clock. Thank you.